Last video closed the chapter on derived distributions with a sampler. Push uniform numbers through the inverse CDF and any distribution you want comes out. This chapter puts expectations to a new use, turning them into bounds on probabilities, and it opens by forging the tool the sharpest bound will run on. In this video, we meet the moment-generating function, one expectation with a dial. We differentiate it and watch every moment fall out, and we work the transform for two densities we know well, the exponential and the Gaussian. Here is the definition. The moment-generating function of a random variable x is the expected value of e to the sx. Read it as a probe. The number s is a dial, fix a setting, and the expectation returns a single number. Sweep the dial, and you trace out an entire function of s that encodes the distribution of x. For a continuous random variable, the expectation is an integral, the density of x weighted by e to the sx, integrated over the whole line. At s equals 0, the weight is flat, and the integral is exactly 1. Tilt s positive, and the weight favors the large values of x. The transform feels the right tail. If you have met the Laplace transform in a circuits or signals course, you have seen this integral before. The moment-generating function is a variant of it, and it strikes the same bargain. Hard operations in one domain become easy operations in the transform domain. The definition covers discrete random variables too. For an integer-valued x, the expectation is a sum, e to the sk, times the mass at k over all values k. That is exactly the ordinary generating function from when sums became products for discrete variables, evaluated at z equals e to the s. Same machine, new coordinates, and as a party trick, it grinds out the mean of a discrete uniform with 2 rounds of Hopital's rule and no special sums. Now the name earns itself. Suppose the transform exists on an open interval around s equals 0 and differentiate it n times. The derivative slips inside the expectation, so we are differentiating e to the sx with respect to s n times over. Watch what each pass does. Differentiating once pulls one factor of x down in front of the exponential, twice x squared. After n passes, x to the n stands in front. Now set s to 0. The exponential collapses to 1, and what remains is the expected value of x to the n, the nth moment read off on demand. In particular, the first derivative at 0 is the mean, and the second derivative at 0 is the second moment. The two numbers every variance computation needs, now delivered by one function. Compute the transform once, and differentiation replaces integration forever after. Time to work one end to end. Let x be exponential with parameter lambda. The transform is a single easy integral. From 0 to infinity, lambda e to the minus lambda x times the probe e to the sx. The two exponentials merge into e to the minus lambda minus s times x, and for s below lambda, the integral evaluates to lambda over lambda minus s. That compact fraction now holds every moment of x. Differentiate once, lambda over lambda minus ss squared. Set s to 0, and the mean appears, 1 over lambda, no integration by parts required. Keep differentiating and a factorial builds up. The nth derivative is n factorial lambda over lambda minus s to the n plus 1, which at 0 is n factorial over lambda to the n. Every moment of the exponential from one integral. The variance rides along for free. The second moment is 2 over lambda squared. Subtract the square of the mean, and 1 over lambda squared remains. The jewel of the catalog is the standard normal. Its density is e to the minus x squared over 2, scaled by the square root of 2 pi. Multiply by the probe, and the two exponents merge into minus x squared minus 2sx over 2. Now complete the square. Add and subtract s squared inside, and the exponent splits into minus x minus s squared over 2 plus s squared over 2. The clean factor e to the s squared over 2 steps outside the integral. Look at what stays inside. A Gaussian density whose center has slid from 0 to s. Sliding a bell curve does not change its area. It still integrates to exactly 1. So the integral vanishes, and the factor out front is the whole answer. The moment-generating function of the standard normal is e to the s squared over 2, the simplest transform in the catalog. One more rule lifts this to every Gaussian. For y equals ax plus b, the transform of y is e to the sb times the transform of x at as. The shift walks out of the expectation, and the scale folds into the dial. Apply it to y equals sigma x plus m, and a affine function of a Gaussian is Gaussian, and the general answer appears, e to the sm plus s squared sigma squared over 2. Differentiate at 0, the mean is m, the second moment is sigma squared plus m squared, so the variance is sigma squared exactly as anticipated. The key idea of this video: one transform packages every moment, compute it once, and differentiate instead of integrating.